Hello everyone, this is Deepal Nayak from St. Xavier's High School, Surat. Our today's topic is Topic 2, Methods of Preparation of Haloalkanes from the chapter Haloalkanes and Haloarenes. First of all, we will study methods of preparation of only haloalkanes. This topic is one of the very important and my favorite topic because in this topic I am going to introduce so many important reactions. The very first method to prepare haloalkane is from alcohol. Here alcohol is the starting material and this reaction is most likely reaction to prepare haloalkanes because alcohol, the starting material, is very easily available and very cheap. Second is the preparation from hydrocarbon. This reaction is a very important reaction which requires so many drastic reaction conditions, but it is also very interesting to study. The third one, by halogen exchange method. Halogen exchange method is very useful method for certain conversion from haloalkanes or haloarenes. And fourth one is from silver salt of acids. This one is very important reaction where fluoride containing haloalkanes we want to prepare. So that we will see later with example. Here there are four major methods of preparation of haloalkanes. The very first preparation from alcohol. We will prepare alcohol using different reagents. The first one, by the action of halogen acid. Halogen acid means HX, where X may be chloro, bromo, iodo. The second, by the action of phosphorus halides, there may be PX3 or PX5, phosphorus trihalide or phosphorus pentahalide. Third one, by the reaction of SOCl2. SOCl2 is thionyl chloride and industrially this reaction is the most important reaction of preparation of haloalkanes from alcohol. Why? That we will see later. Second, preparation from hydrocarbon. Here hydrocarbon alkanes and alkenes will prepare haloalkanes from alkanes and alkanes. And as you know, alkanes are the saturated hydrocarbons. So here we use free radical halogenation, that is substitution reaction, and alkenes are unsaturated hydrocarbons. So here we use addition of HX and addition of X2. HX is halogen acid and X2 is halogen atom molecules. By halogen exchange method, here we learn the specialized reaction called Finkelstein reaction and Schwartz reaction. And fourth one is from silver salt of acid. This reaction is also called Borodin-Hunziker reaction. Now we see our first method of preparation of haloalkane is preparation from alcohol. There are three methods to prepare haloalkane from alcohol. The first one is by the action of HX halogen acid, by the action of PX3 or PX5 phosphorus halide, and by the action of thionyl chloride. First we see by the action of HX, we prepare haloalkanes from alcohol. The general reaction can be given as ROH. This is alcohol. This reacts with halogen acid, which is represented as HX, to give RX alkyl halide and water as byproduct. So in any chemical reaction, it is compulsory to write the name of each reactant and product. This is alcohol, our starting material. This is halogen acid, which gives haloalkane and water. Now we see the example of different type of haloalkanes. Generally, this rate of the reaction depends on the nature of alcohol. They may be primary, secondary or tertiary, and of course on the strength of HX, halogen acid. They may be HCl, that is hydrochloric acid, or HBr or HI. First we use hydrochloric acid to prepare haloalkane from the alcohol. If primary and secondary alcohol reacts with hydrochloric acid, this is comparatively slow reaction which requires catalyst ZnCl2 zinc chloride, and in presence of catalyst this reaction gives primary haloalkane and secondary haloalkane respectively. With example, we will try to study these two reactions. For primary and secondary alcohol, CH3, CH2, CH2, OH. This is primary alcohol and the name of this alcohol is propanol. Propanol reacts with HCl in presence of catalyst ZnCl2, of course anhydrous. Why anhydrous ZnCl2 is used here? Here alcohol is present. If the water molecule is present in with ZnCl2, the rate of reaction becomes slower. Anhydrous ZnCl2 helps to break this CO bond, and this OH will replace easily with X of halogen acid. Here chloride is present in hydrochloric acid, so our product will be CH3, CH2, CH2, Cl. This is primary propyl chloride, and byproduct is water. For secondary alcohol, CH3, C, CH3, here H and OH. Here you can see that OH containing carbon is attached with another 2 carbon. So it is secondary carbon, and this one is labeled as secondary propyl. Why propyl? Because here 3 carbons are there. So secondary propyl alcohol, which reacts with HCl in presence of anhydrous ZnCl2 to give secondary propyl chloride like CH3, CH, CH3. Here breakdown of CO bond, OH will be replaced by chloride functional group and H2O is the side product. So the name of our product is secondary propyl chloride. The rate of the reaction of secondary propyl alcohol is faster with compared to primary one. Therefore, if we take HCl, concentrated or dry HCl gas, this may be faster. The rate of the reaction of tertiary alcohol is the fastest, or we can say that reaction with tertiary alcohol is the rapid reaction in which no catalyst is used. Just stirring is required to convert alcohol, tertiary alcohol, in the tertiary alkyl halide. So now we see the example of tertiary alkyl halide. Here secondary for primary and secondary alcohol is used to prepare primary and secondary alkyl halide, and the examples are given. With tertiary alcohol, the reaction is very rapid, so no need to use catalyst like ZnCl2. Here CH3C, CH3, CH3, OH. 1, 2 and 3 alcohol containing carbon attached with another 3 carbon. So this is tertiary alcohol, and the name can be given as tertiary butyl alcohol. The reaction of tertiary butyl alcohol with concentrated HCl is very rapid, and this reaction occurs at room temperature only. Just stirring with concentrated HCl will have CH3, C, CH3, CH3, Cl. This is tertiary butyl chloride plus HCl. So here, according to the type of alcohol, we can say that the rate of the reaction is tertiary is greater than secondary, which is greater than primary. This reaction is very important reaction in laboratory also. You can classify, or you can detect primary, secondary and tertiary alcohol using this reaction. In laboratory, this reaction is known as Lukas test. Now we see what are the observations of Lukas test. How can we detect primary, secondary and tertiary alcohol using this test? See, if you add concentrated HCl and heat the reaction mixture with in presence of anhydrous ZnCl2, and immediately you get oily drops. The conclusion is that tertiary alcohol is present. If you get milky mixture after 5 minutes, the conclusion is your alcohol should be secondary one. And if no change in the reaction, that means no reaction after long time, that is the primary alcohol. So the rate of tertiary alcohol with concentrated HCl in presence of zinc chloride is faster. Secondary is slower, and primary will not react actually, or the reaction is very difficult, we can say. So the reaction of primary and secondary alcohol in presence of anhydrous zinc chloride with HCl is also known as Groves reaction, GROOVE, Groves reaction. This can be asked in MCQ, and this reaction is in the syllabus of JEE and NEET. So this question can be asked in JEE or NEET examination. So be careful. Now we see the preparation of bromoalkane from the alcohol. For the preparation of bromoalkane, we use HBr 48%. 48% HBr, hydrobromic acid. If alcohol is heated with vigorous shaking and boiling in presence of 48% HBr, we have bromo derivative of alcohol. For example, CH3, CH2, OH, which reacts with HBr 48% in presence of concentrated H2SO4. Here concentrated H2SO4 is catalyst. Catalyst is always written in the square bracket. This is the style to write chemical reaction. And the yield is CH3, CH2, Br plus water. Now we label all the reactants and products, which is very, very important. I repeat, ethanol, HBr, hydrobromic acid 48%. This is catalyst which gives bromo ethane. Here H2SO4 acts as catalyst, so at the end of the reaction it is regenerated and we can use it again as catalyst. Now sometimes HBr is in situ. Now here another word which you must be familiar with, this word. This is in situ. Actually this is a Latin word which means at the same place or site. There are so many reactions in chemistry, in synthesis actually, in organic as well, inorganic chemistry, that some reactants are generated inside the solution. They are not the static material or we cannot add it physically. But these reactants produce inside the reaction during the chain reaction or as the intermediate. Now I will give one example. You will be very clear that here we are using the starting material alcohol, of course, because it's the preparation from the alcohol. In alcohol we add concentrated H2SO4 and be very careful. This here concentrated H2SO4 is not a catalyst. Why? Because this concentrated H2SO4 reacts with KBr, or you can take NaBr also, but actually potassium bromide and sodium bromide is very expensive. That's why we prefer generally this reaction, but this reaction is very useful sometimes if the concentration of our alcohol is very less or HBr is not available. Okay, now concentrated H2SO4 reacts with KBr in situ. That means in the same place in the reaction to form HBr. And by heating we will have the same product CH3, CH2, Br. The side product is KHSO4 and water. Potassium bisulfate is also very important reagent that you will study in aldehydes and ketones. Actually this reagent is used for the purification of aldehydes and ketones in the laboratory. That we will study in that chapter. Here you just concentrate what is in situ reaction and how HBr produced inside the reaction or during the reaction. Now label all the reagents. Okay, so here we have two ways to prepare bromoalkane using HBr or using combination of H2SO4 and KBr or NABr, because this reaction is inside reaction where the reagent produced inside the reaction. Inside, or we can say during the reaction. They may be intermediate, or they can generate in the form of reagent only. Now we prepare iodoalkane from alcohol. Iodoalkane can be prepared by heating alcohol and 57% hydroiodic acid. The mixture is constantly boiled, reflux to give iodoethane and water. This is ethanol, which is heated with 57% HI and by reflux method to give iodoethane. Another way to prepare iodoalkane is the reaction of alcohol with the mixture of Ki and H3PO4, that is phosphoric acid 95%. This one is also in situ reaction where HI is prepared inside the reaction during the reaction. So we see the reaction. CH3CH2OH reacts with Ki and 95% H3PO4. This is phosphoric acid. By the combination of these two reagents, we have HI inside the chemical reaction. So it is inside to reaction to give CH3 CH2I, iodoethane, KH2PO4 byproduct and water. We'll label all the reagents and products. Ethanol, potassium iodide, phosphoric acid to give iodoethane. Actually, this is the most likely method to prepare iodoethane. Because this reaction gives maximum yield. So, industrially, iodoethane can be prepared by the combination of ethanol and mixture of Ki and 95% H3PO4 to give iodoethane or iodoalkane and byproducts. These byproducts are also very important in the further chemical reaction as starting material or as the purifier. Here we have some important notes regarding the preparation of haloalkanes from alcohol by using this method. The first one, reaction with HX. These notes are very important when you are solving MCQs especially. The note number 1 is this method is not applicable for secondary and tertiary iodo as a bromoalkane preparation. Why? Because if we use this reaction to prepare secondary and tertiary iodo and bromoalkanes in presence of concentrated H2SO4, the product will undergo dehydration, and that's why we have product alkene instead of haloalkane. So, if the secondary or tertiary iodo or bromoalkane we want to prepare, wherein we cannot use concentrated H2SO4 and it is quite difficult to prepare. The second, the order of reactivity. This type of questions are most likely questions in JEE as well in NEET. See here the reactivity of alcohol very initially of the in this topic I have said that the rate of the reaction is depend on the nature of alcohol as well the strength of halogen acid. So it is given here. The order of reactivity with respect to alcohol is tertiary, secondary and primary. Tertiary alcohol is rapid, then secondary and primary gives very slow reaction. And with halogen acid, with respect to halogen acid, HI is the fastest, HBr faster and HCl needs generally catalyst. Now second method to prepare haloalkane from alcohol by the action of pX3 or pX5. First we see the preparation of chloroalkane. Preparation of chloroalkane using PCl5 and PCl3. So for this, first I introduce the general reaction. Starting material is of course alcohol, ROH reacts with PCl5 to give RCl, chloroalkane, POCl3, phosphoryl chloride and HCl. Now we label all the reagents and products. This is alcohol, phosphorus pentachloride PCl5, chloroalkane. This is also called phosphorus oxychloride or phosphoryl chloride and HCl. Here you can see the balance reaction equation. It is very important in theory examination that your reaction should be balanced. If your reagents and products are right but the reaction is not balanced as well, the reaction condition is not given, that means your reaction is not right because the product will not produce. So it is very important. Just write the reaction is not important, to balance the reaction equation as well. Labeling the reagents and products with the proper reaction condition gives full marks. Otherwise 0.5 or 1 mark you will lose. Now another general reaction using PCl3. 3 moles of ROH will take, because here we have PCl3 3 moles of chloride to give 3 moles of RCl, plus here our byproduct is very important, that is H3PO3 phosphorus acid. Labeling alcohol, phosphorus trichloride, chloroalkane and phosphorus acid. Now we take examples of each reaction. Reaction number 1. So for reaction number 1 we'll write CH3CH2OH ethanol reacts with PCl5 to give CH3CH2Cl chloroethane, phosphoryl chloride and hydrochloric acid. Ethanol, phosphorus pentachloride, chloroethane, and phosphoryl chloride. For reaction number 2, the example is 3 moles of CH3 CH2OH ethanol reacts with PCl3 phosphorus trichloride to give 3 moles of CH3 CH2Cl plus H3PO3 phosphorus acid. Now we label all the reagents and products. Ethanol gives chloroethane and phosphorus acid. So here the reaction of PCl5 and PCl3 to give chloroalkane. Now we see the preparation of bromo and iodoalkane from PBr3 and Pi3 respectively. The general reaction can be given as ROH alcohol. Here PBr3 and Pi3 both are prepared inside the reaction during the reaction of red phosphorus and X2. Here X may be Br and I. That means if red phosphorus reacts with Br2, it will produce PBr3 inside 2 and gives RBr, that is bromo derivative. If red phosphorus reacts with I2, that is iodine, gives Pi3 inside 2 to give iodo derivative. Now we take example CH3 CH2OH. This is ethanol. Ethanol reacts with red phosphorus and Br2 combination. So this in situ reaction produce PBr3. That's why inside the reaction here ethanol reacts with PBr3 to produce CH3 CH2 Br, bromo ethane, and in presence of red phosphorus and I2 inside the reaction, the combination produce Pi3. That's why our product will be CH3 CH2 I, that is iodoethane. Here the possibility we can say primary bromoalkane and primary iodoalkane only. So here is the preparation of haloalkane, that is chloroalkane, bromoalkane and iodoalkane from alcohol using PX5 or PX3. Now we see the third most important and most likely used method of preparation of haloalkanes from alcohol, and that is by the action of SOCl2, that is thionyl chloride. Alcohol is reacted with SOCl2 thionyl chloride in presence of pyridine as catalyst is chloroethane, that is haloalkane. The byproducts are SO2 and HCl. We label all the reagents and products. This is ethanol. This is thionyl chloride. In formula of thionyl chloride SOCl2. O is also capital. It is not small. So be very careful. Thionyl chloride SOCl2. Pyridine means this reaction occurs in the basic medium, because pyridine gives basic medium to the reaction, and this gives chloroethane. Okay, why this reaction is very important, or industrially this reaction is very useful to prepare haloalkane? And the answer is here in the reaction. You see SO2 arrow, HCl arrow, means these two byproducts produced in the form of vapor. That means in gaseous state. So it is very easy to remove these two gases from the reaction mixture, because these byproducts are escapable. That's why chloroethane in liquid state we can extract easily. That's why this reaction is mostly used industrially, that is commercially, to produce haloalkane. And another reason is SO2 and HCl. Both are very important byproducts. SO2 further goes in the preparation of concentrated sulfuric acid in contact process, and HCl is used as starting material or as a solvent, or to purify so many equipments in the laboratory. That's why this reaction is very useful. But here there are some limitations of these three methods. All these three methods have limitation, and the limitation is we cannot produce haloarene from these three types of reagent. Why? Because haloarenes, the structure you know. In the haloarenes, the CX bond fills a partial double bonded characteristic because of the strong electronic cloud on halide functional group, and that's why this bond is quite stronger, and it is not easy to break using these three reagents. These three reagents means HX, PX3 or PX5 or SOCl2. With the help of these three reagents, we prepare only haloalkanes.